So I'm going to talk about turning algebras as origami constructions. So this is kind of a nice way to construct different spaces like Quaternion algebras or any lattices. So the way this is going to be structured is first I'll kind of just show the complex number case, and then we'll kind of see how it generalizes to higher dimensions. And so just to start, so what I mean by origami is that we have a set of angles or directions, and at first we'll think about it in the complex plane. So our angles will be represented by points in the plane. And then, well, it's not going to be exactly like the origami you may think of with folding, but there is still some aspect of folding, which is these lines through the plane. So just a crane just for fun. So what we do is when we have two different points, and we take two different lines, they have an intersection. And so let's start out with a quick example in the complex plane. And like I said, our angles are going to be represented by points. So the point represents the angle in the direction of that point from the point. So here's an example to start. We start out with pretend this is the complex plane, and it says 5, but our points that we start with are 0 and 1. And we have a set of allowed angles. So in this example, the allowed angles would be 1, I, and I plus 1. So 1 is the horizontal one, I is the vertical one, and then I plus 1 is diagonal. So we can just draw some lines through those points and see what happens. So that's one of our allowed angles, right, vertical, and then do the diagonal one to the point 0, and we get an intersection. All right, so now that becomes another point in our set. And so what we're doing is we're creating this set of points, and we're going to look at what properties this set of points makes. You know, is it a lattice? And then we can talk a little bit about multiplication as well. And when we generalize, that's where we get into Quaternion algebras. So let's do a couple more. Remember, vertical and horizontal are both allowed angles, so we can make our fourth point there. Fifth point there, sixth point there, and so on. Eventually we get the Gaussian integers. So that's a really nice set. It's a lattice. It's also a really nice order. So this is sort of our goal, to sort of recreate higher dimensions. Okay. So let's jump right into n dimensions now, and then we'll kind of come back and look at 4 dimensions. So for now, all we really need is the additive structure. So we're going to let V be a vector space, call it Rn. And we're going to first define what we mean by intersection, kind of formally. I showed you the little demo, but this is the formal definition. Is we need 2 points, P and Q, and through those 2 points, we'll have 2 angles, alpha and beta. And so what we do is we are going to draw the line through the point P at the angle alpha, and we're going to draw the line through the point Q at an angle beta, and we're going to record their intersection. Okay, so our line is a set of points in the form P plus R alpha, and Q plus R, S beta respectively. So there's our points P and Q. Alpha is going to be that direction, so we draw a line to P, and same with Q. And then there's our intersection right there. And the notation we use is this double bracket notation for the intersection of the line through the point P and Q at angles alpha and beta. Or the intersection of the lines through point P and point Q at angle alpha and beta. Okay, so this whole game is just a bunch of drawing lines and recording their points of intersection. So in order to do this, we need a set of allowed angles and directions. Okay, so we're going to call that set U. And we're going to, again, use points in our vector space to represent the directions. And we kind of abuse notation a little bit while we're only looking at the additive structure. And it'll make more sense once we get back into algebras. But in complex numbers, it's a two-dimensional real vector space. And we think of the point 1 as like 1, 0, right? It's if we want to think of it as R2. So when we say 1, we really mean the first basis vector, 1, 0, 0, up to however many dimensions we have. And then 0 is just the 0. Okay, so the iterative process that we use to define the set of points is M1 of U is the set of all initial intersection points, which means we just have our two starting points, 0 and 1, and we just draw all the lines through them at our allowed angles. That gives us a set of points. Now, once we have that set of points, that's an even larger set than just 0 and 1. So now we can do this again, but now we have more points. And then we just keep creating more points and more points until we get our whole set. Okay, so after the kth iteration, we take that set of points and draw lines through those and intersect them. And then in the end, we take the union of all the points we get in each step of the process. Okay, so what I'm going to do now is show you an example. All right, well, this is the example you saw before, the Gaussian integers, and this is our set U of allowed angles. But we can also create some Quaternion orders in here, so that's nice. So let's just take our Hamilton Quaternion algebra, and let's let our set of angles be 1, I minus 1, j minus 1, and k minus 1. So essentially, well, it's hard to picture 4 dimensions, but if it were 3-dimensional, we'd have like horizontal this way, vertical, and then another dimension, and then we have a bunch of diagonal directions. And what happens when we have diagonal directions is that they intersect right at the sort of integer coordinate points. Okay, so this gives us the Lipschitz order, which is, well, it's not quite the analog of the Gaussian integers because it's not maximal, but it is a really nice order that we can construct in this way. And one way to see it is that we already get the Gaussian integers with the first 3 angles. And then, well, I and j are kind of, they behave pretty similarly. So 1, j, and j minus 1, you get the same thing in that plane. And then when you sort of combine, it's always closed under addition. So you get the whole Lipschitz order. And then, well, like I said, the Lipschitz order is not the nicest order in this Quaternion algebra. We want maximal order. So let's take the Hurwitz order. And I should mention here that our angles can be scaled. Usually we like to scale them so they're unit length. If they're not scaled, it's for simplicity on the slides because it can get kind of messy when you have a bunch of square roots in the denominator. But it doesn't really matter what you scale, it's all up to scaling. So in order to make the Hurwitz order, we want to take the angles, the first 5 angles that we had before, and then the last 2 angles, instead of k minus 1, we want to use the 1 plus I plus j plus k over 2, and 1 minus I minus j minus k over 2. And if you think about those last 2 angles, if you look at just the first 2 points, 0 and 1, and you intersect the 2 lines through those 2 points in the last 2 angles, it'll get you that last basis element of this Hurwitz order. So it's kind of nice to be able to construct the order in this way. And for those of you interested in coding it, this could be, you can make an algorithm of this. All right, and then the nice thing when we do have a multiplication structure, like in this Quaternion algebra, or in these two orders, is that, well, when you have two lines and you intersect them, usually it's solving an equation, setting P plus R alpha and Q plus S beta equal to each other. But if we have a multiplication structure, we actually can have a formula that you just plug in the 2 points and the 2 angles and it pops out the intersection point. So that's one nice thing that happens when we have a multiplication structure. And then I'll really briefly talk about our results and then just give it a little more angle with, or motivate a little bit more why, how this is nice for Quaternion algebras. So, okay, well first I should acknowledge what has been done previously. So Bueller, Butler, Maloney, and Graham, they sort of first studied these in the complex plane. And one of the most important properties is the additive closure of this origami set and review. That's really important in order to get a lattice and order. And then Drinko and Bueller, they talked about the multiplication structure in 2 dimensions in the complex plane. And then Jürgen was a student of Adriana's, who's here today. And I should have mentioned, this is Jürgen was a thesis student of Adriana, and they studied a little bit about this also in the complex plane and how to construct certain rings of integers in imaginary quadratic fields. And we need it to be imaginary because we really need the two axes. And then, so this is kind of how this project came about. So Davina, another thesis student of Adriana, was also studying these origami constructions and looking a little bit about what might happen in hyperbolic space. But then the 3 of us sat down and really thought about how do we generalize this to Quaternions and just higher dimensions in general. So half the problem was figuring out how to define intersections when, well, now in higher dimensions you can have skew lines. They won't always intersect. So here's our main results. It turns out, in any real vector space, you can take a lattice. So it's going to be generated by 1, and then the basic element tau 1 to tau minus 1. And there is a certain set of angles that we can use in order to construct that specific lattice, which is really nice. We can take whatever lattice we want and construct it in this way. Okay, so that set of angles, the angles kind of come in pairs because you need 2 angles to make an intersection. So each time you add a dimension, you need 2 angles to get to that dimension. And then there's some other things that happen. So what if we make a lattice with a set of angles? Well, what if we introduce another angle to our set? And we're now allowed to use that angle. 3 different things could happen. Maybe nothing changes. Maybe that new angle is sort of, only intersects at points we already had in our set. Or maybe if you really carefully construct this new angle to add, maybe it's just pretty much skewed to all of the other lines we made. So no intersections will be introduced. So another thing that could happen, well, if we had a lattice, it could become a finer lattice. We could add, some extra points, but not enough points to make it all dense. Or it could just make the whole thing dense. So those are our 3 options. And there are scenarios when all those options can occur. Okay, so let's just do a quick example of that. So here, you can think of us as being in the Quaternion algebra. If we take our angle set to be the angle set we used to create the Lipschitz order, z plus di plus bj plus bk. Then we can add one more angle, which is 1 plus I plus j plus k over 2. Now that angle alone isn't enough to get us any new points of intersection. So we actually, nothing happens. We get the same line back, or the same order. Going one step further, adding one more angle. Now we're getting a Hurwitz order by just adding the sort of conjugate to the first angle we introduced. So that's a finer lattice. And then I haven't talked a lot about results in 2 dimensions, but if we add the angle I plus 1, that's another diagonal angle. So what's going to happen is it kind of has this fractal-like property where, well, we get all the integer coordinate points, but then when we have 2 diagonal angles, they intersect at half and half. We can draw a line down the middle and get just a point and a half. And now that we have 0 and half, we can just do the whole thing again and get a quarter, an eighth, and a 16th, and so on. And we can do this in any sort of corner of the picture. So this is a dense set now. Okay, so all of these can happen. All right, so that's pretty big. This is kind of cool to see what happens. And I know I'm running close to the time, but
you have time.
I'm going to take a couple more minutes.
Go ahead, keep going.
Okay, so I want to just a couple more slides to really get at the Quaternion aspect of the multiplication structure. So in 2 dimensions, to get our lattice, we need 3 angles. And when we use 3 angles, the lattice we get is essentially the lattice generated by the intersection point with our 2 angles that are not the horizontal angle. So the alpha and the beta, those are the 2 angles that will make our intersection point. And that point we call tau. That's the second basis element for our lattice. So to tell if this lattice is closed under multiplication, or in other words, it's in order, we need to check whether tau squared is in our set as well. Because, well, we need the product of any 2 elements in our set to be in our set. Well, 1 is the other basis element, 1 times anything else is just itself. So that's what we need to check. And then, if we wanted to generalize this to Quaternion algebras, we would need to, well, we know how to make a given lattice, right? So if our angle set is of this nice form with our 7 angles, 7 is the magical number in 4 dimensions, we can use our angle set to determine the set of basis elements, and then pairwise tell if the product of each basis elements is in our set. So that's kind of nice. So that gives us, if our angle set is the nicest way we can possibly make it, there's a way to check. Although it feels kind of like cheating because we can just make the lattice we want. So then the question is, can we just do this no matter what our angle set is? Well, our angle set, in order to make our lattice in, say, 4 dimensions, we do need at least 7 angles. In n dimensions, it's at least 2n minus 1 angles. But it's not to have at least that many angles. We may not be able to reduce the angle set just to 7 angles, or 2n minus 1. So that's unfortunate, but that gives us more information. So here's an example in 3 dimensions. Maybe those of you in the audience are screaming about there's no k in there, so there's not multiplication anyway. But the point of this example is that we can't, from this angle set, we cannot pull out 2 of our angles to get an angle set that still is the whole lattice. This is 3 dimensions, so our magic number is 5 angles. We can't take any subset of 5 angles to get our lattice. So there's still more then this is just a kind of quick guess, is that after n iterations of this origami construction process, my guess is that that's how many iterations it'll take to get all the generators of our lattice. And then we can go back and use the same method of just pairwise multiplying each pair of generators. So that's a guess. And if this is true, that's only a finite number we can test. So that could be coded. You know, it wouldn't take too many steps. And that could test whether it's closing or multiplication. And there could be a lot more out there. All right, so I will end it here. I think, yeah, we could write a code for this. Yep, so I'll end it here. I think I put this as the last slide, just in case of time. But thank you very much. And thank you for your patience with the technical difficulties of doing it
Okay.
as well.
Thank you so much. Thank you. That was such a beautiful talk. I really liked it. Does anyone have any questions?
I have two questions, okay?
Go ahead.
Sure. So the first one is, in your dad's example, you order to get a sort of quadratic, the denominator is power of 2. So is other quadratic phenomena also possible to happen? Maybe denominator of power of 3.
In the denominator?
Yeah.
So we really need our lattices to be Z lattices because it's closed under addition, which is integer, integer scalar multiples of the points that we already have. But I haven't thought about it in terms of denominators very much because our angles can be scaled however we want. But you could still make the order that's like 1 plus I plus j over 3, with I plus j over 3.
Right, but yeah, I guess usually the thing is there could be scaling, but I think like there's one thing I want to ask is because if this is really dense, because it is not a lattice, and you have to infinity many times taking the division by 2. Right? So when you ask how many times the infinity divide, then in this case the 2 just stands out.
Yeah, so you could make a dense set with all the like 1/3, for example, 1/3, 1/9. So you could make that.
Oh, you can make that just with infinitely many things, right?
Yeah, you can. It'll just be dense, but yeah.
Is there an idea like how does it work? You mean that there are a finite set of angles where you can use that to make, for example, 1 over 3 n power 1 by z2. You can make that with finite set of angles. Is it true?
Sorry, are you saying over?
So let's say you have 2 dimensions. Is it true that you can use finite many angles to make the set that is 1 over 3 infinity times z2?
Yeah.
Oh.
Yeah. So you can kind of just draw any point you already have. You can kind of just draw the line that intersects the horizontal line at 1/3. So you could take, say, I minus 1. So you get the Gaussian integers, and then take the point I plus 1, and draw the line, introduce the angle from I plus 1 over to 1/3.
Oh, yeah, for the benefit of us, is there a structure theorem to all the possibilities?
I apologize for interrupting, but we need to get to the next speaker. Okay.
Yeah.
Okay. Thank you again.
Couple more.
Yeah.